We have several calculations to make in this week's work. I'm going to do several of them for you, but not all of them. Some of them are rather tedious. You have to write a lot of numbers, make a lot of calculations, but none of the calculations are what I think is overly difficult. One thing you want to be sure to be able to do is calculate standard deviation. Standard deviation is that most important measure of dispersion that we will use, and it's a very common one. How's it done? Well, first of all, we need some data, and I've drawn a number line, and I've drawn some measurements that I made. And let's say I've measured the length of a whole bunch of people's pinky. Can't spell it. Pinky length. And let's say, well, let's see, what did I get? One person had a short pinky. It was only 1 inch long. A couple of them were 2 inches long. One was 3 inches long. A couple were 4 inches long, and one was 5 inches long. Well, if you have a good eye, you can see just by looking at this data set that the mean is at 3. We'll prove that. Let's see how to calculate standard deviation. Well, first of all, we need to make some sort of a table where we're going to list our values. We're going to calculate the deviation from the mean, and we'll symbolize that as x minus x bar. And then we're going to also calculate the deviation squared. Deviation squared. And so that means we take our value in the prior column, our x minus x bar, and we simply square that quantity. Well, first of all, we need a mean. Am I falling off the paper? Sure am. Let's move that down here. X bar. We need to sum up our values and divide by the number of values. How many do we have? 1, 2, 3, 4, 5, 6, 7. Now let's put our values down. We have 1, 2, 2, 3, 4, 4. Oh, shoot. This is not going to be pretty. All right, I'm going to get a different piece of paper. Try that again. Tyler suggested I get a whiteboard, and I'm going to ask Santa for a whiteboard because that would make this easier, wouldn't it? Thanks for that suggestion, Tyler. Okay, sample stand, or our mean is coming down here. Let's see, x bar is going to be something over 7. We're not sure what yet. Let's list my values. I've got 1, 2, 2, 3, 4, 4, and 5. And I'm going to leave some room. You'll see why. Let's add these up. We got 9, 13, 16, 17, 18, 19, 20. We have a total of 21. Oh boy, look at that. 21 divided by 7. We have a mean of 3. Sure enough, our mean is at 3. And I'll write x bar equals 3. Didn't plan too well for space again. That's what happens. Okay. So let's see. Now we have to calculate the difference between our x values and the mean. So our mean is 3. Well, 1 minus 3 is negative 2. And 2 minus 3 is negative 1. 2 minus 3, negative 1. 3 minus 3 is 0. 4 minus 3 is 1. 4 minus 3 is 1. And 5 minus 3 is 2. And now we have to square those values. 2 squared is equal to 4. 1 squared is 1. I mean, negative 1 squared. And negative 2 squared. Whatever. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 1 squared is 1. And 2 squared is 4. And now we're going to have to add those up. Because recall, we needed, or no, we haven't written out our standard deviation equation yet, but we're going to need the sum of all of the x minus x bar squared values. The sum of the deviations squared. And so let's see, this is equal to how many? 4, 5, 6, 7, 8, 8 and 4 is 12. Something doesn't seem right. Let's add up our mean. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, 20. Oh yeah, that was right. Okay. Did I do these right? 2 squares, 4, 1, 1, 1, 1, 4. 8, 9, 10, 11, 12. Okay. Now, let's scoot our paper up. And let's calculate our sample standard deviation. Abbreviated S, and it's equal to the square root of this value we just calculated, the sum of the deviations from the mean squared, divided by n, the number of data points, minus 1. And if you're curious why that minus 1, where that came from, well, it has to do with assumptions we make about sample versus population statistics and the normal distribution. It takes some intense statistics to really understand why. Just accept it. Okay, so our values are going to be the square root of 12 over, let's see, how many values did we have? 1, 2, 3, 4, 5, 6, 7. 7 minus 1. That's 6, which means we're looking for the square root of 12 over 6, or the square root of 2. And the square root of 2 is 1.4. Okay, we calculated the sample mean equaling 3. And we just finished calculating our sample standard deviation. We calculated 1.4. Recall that from our normal curve that with a mean, and let's see, in our case our mean was 3, and out here at plus or minus 1 standard deviation, we should get 68% of all values between those two values. Well, for our sample, how much is that? If we add 1.4, our mean plus 1 standard deviation is going to be 4.4, and standard deviation, or I'm sorry, mean minus 1 standard deviation is going to be 1.6. Is that right? 2, 3. Yes. So what does that tell us? If we look at our distribution of data, we should find approximately 68% of the values between 1.6 and 4.4. Well, let's go back to our number line and let's mark those points. Let's see, 4.4. There's 2, there's 4, 5's in the middle, so 4.4 is somewhere like that. And 1.6, let's see, there's 1, 1.6 is going to be somewhere in here. And now let's count how many values we have. Well, let's see, we have 1, 2, 3, 4, 5 within, and we have 2 outside. We have a total of 7. We have 5/7 being within plus or minus 1 standard deviation. What percent is that? I apologize, I forgot to hit the record button and just started talking for the last few minutes, so let me get caught up. In our problem, we calculated a mean of 3 and a standard deviation, sample standard deviation of 1.4. What does that mean in terms of where our data are located, where we might expect them? Well, let's go back to our normal curve. And if we draw a normal curve, and if we drop down lines at plus 1 standard deviation and minus 1 standard deviation, we know that 68% of the values will be contained within the range from minus 1 standard deviation to plus 1 standard deviation. But now we have real values, and let's calculate and see how these things turn out. We know our mean is 3, and so I've written 3 here. And now that we know our standard deviation is 1.4, we can write in that the mean plus 1 standard deviation is equal to 4.4. And 3 minus 1 standard deviation is equal to 1.6. So now we should be pretty comfortable saying, if all these stats work out, that 68% of our values in our data set should fall between 1.6 and 4.4. Well, let's see if it works. Let's go draw in those points, 4.4 and 1.6, and see what we get. Well, you can see I've already done that. I went from our mean of 3 in the center here, 3, there's 4, and halfway between 5. So I drew a line at approximately 4.4, and I drew another line at approximately 1.6, which was, that's 3, 2, 1's in the middle. Yeah, that's roughly 1.6. And I counted how many data points I have between those two plus or minus 1 standard deviation. And I have 1, 2, 3, 4, 5 points out of 7. And I calculated that 5/7 is 71% of our data. Now that's not quite 68%. And why isn't it? Any guesses? Well, it's because we have such a small sample size. If I had 10,000 data points, I bet we'd be very close to 68%. If this was truly a normal distribution. What is our data again? It's the length of the pinky. Boy, my pinky is only about 2 inches long, and I have big hands. I don't know how they ever got a pinky length of 3 inches, but that's besides the point. Okay, I'm trying to put some realism into this problem, and looking at our data sets, hopefully that 68% and putting it in terms of our actual data means something for you.